So, good morning again. Let me summarize and complete a couple of things that we were discussing yesterday. So I hope it didn't go unperceived, but we defined this important notion of luminosity that together with the energy is the very basic parameter that any collider should specify for you to be able to start understanding what could be the physics that you can do with this collider. It is defined very easily as for us in the sense that it's just a factor you have to multiply the cross-section for in order to have the rate, so the number of reactions of a certain type that correspond to a certain cross-section that take place in a certain amount of time. And I sketched the formula for luminosity, and also this gives you the scheme in which particles collide. The particles are put into bunches. These bunches are these sets of particles, which are physical, very large number of around, in this case, 10 to the 11 particles, which are more or less localized in the same place, and they move more or less with the same energy, and they collide head-on. In the case of LEP, this was, let's say, E minus, and this was an E plus bunch. The bunches are spaced in some way, right? Now, depends on the details, but from one bunch to another, there is a certain amount of time that passes, which is the inverse of the frequency, okay? That then makes that at the IP, so IP means interaction point, they collide with a certain, so a certain number of collisions obtained for a given time, and this should be counted by this factor 1 over time, or F, in the luminosity formula. Then there is just the number of particles of both bunches, and there is the area, the effective area of the beam, which is in this direction. So the area in the 2 dimensions, so the area here, right? Because it's the surface, each beam sees the other beam, right? They overlap like this, and so that's why the smaller it is, the more dense the beam is in the transverse direction, and so the more chance there is to have a collision, right? We could discuss what are the limitations to make this A going to 0. It's an interesting topic about beam dynamics, has to do with a parameter called emittance, which is a conserved quantity in non-dissipative system, and such that you can squeeze this particle up to a certain extent, and that's related with this. So it's very interesting and beautiful, actually, to see how these numbers can be engineered to bring a luminosity that is high enough for us to do some interesting physics, to have some events to study. So here I was lucky. I put in some numbers from LEP, well, like the frequency, like the vertical and horizontal beam dispersion, sigma x and sigma y, that give you the area, okay, like 4 pi sigma x times sigma y gives the area. The numbers, I've taken this from some table, and I got a very similar result to the actual instantaneous luminosity. That's also called instantaneous luminosity, this L here, of LEP, which is around, it's measured in these units, inverse, so centimeters to the -2, seconds to the -1, and it's around 10 to the 31 centimeter to the -2 seconds to the -1. One also likes to write things in terms of the integrated luminosity. So you normalize it to 1 year of run. So that's the same formula, but this is considering a time not of a second, but of the inverse, so inverse time of 1 year. So collider physicists call a year to belong 10 to the 7 seconds, while the year is in fact a bit longer than 10 to the 7 seconds. And they believe that this is a reasonable estimate of how much time during the year the collider is in fact operating, right? And so we typically have this number, like the integrated luminosity per 1 fictitious year of 10 to the 7 seconds, which gives, in this case, something like 2.5 times 100 of inverse picobar, okay? And so if you want to estimate the number of events in total that you get, you take our typical cross-section. I told you that typical cross-section is around 10 picobar, but then it's boosted by a big factor from the resonant enhancement on the peak of the Z of around 1,000. And this, if you multiply it by 100 picobars, gives you a huge number of events, around 10 million sort of events for each different species of Fs that you can have, of fermions that you can produce. Okay, this means that you are able, with these statistics, with this number of events, to make measurement that can be as precise as 1 over the square root of the number of events, which is well below the per mil level. Okay, so it allows per mil level measurements of this cross section, and so per mil level measurements of these fundamental parameters, the couplings, that then we can compare with the standard model. Now, in fact, if you look at the time it took LEP to take these 10 million events, it's more 6 years than 1. Okay, so I'm not sure if, and in spite of the fact that the luminosity, instantaneous luminosity, is correct, so maybe this number is a bit generous. The collider effectively runs less than 10 to the 7th second, but in the case of LEP, there is also the need of changing the energy from one range to the other, because the energy was not fixed, and so maybe that's also why. But still, that's the more or less the statistics of data collected at LEP. Right, so so here I'm showing now, I'm starting from some slides that you have here, and you also have on the GGI webpage. This is some references about basics of standard model theory, of collider, other collider physics lectures, in fact at GGI, some more about experimental physics at LEP and accelerator physics as well, and well, and this is, references, but this will be needed for other topics that we will cover later. Now, here you have the drawing of LEP. You see this mouse, and so it's the same drawing as the LAC because it's the same tunnel. It's gigantic, of course, as you see. These are countries, right? So the scale here is the one of the countries. There is a table of parameters that in particular give you the integrated luminosity, so the actual luminosity times the actual runtime, and you see that it's way below this estimate, in confirmation of the fact that in 1 year you could actually take less, while the instantaneous luminosity matches with this expectation. So the energies you see, this is the beam energy, so the center of mass energy is twice. So this is very close, if you multiply it by 2, to the mass of the Z boson, and so this corresponds to the runs that were made on the Z peak, the Z pole runs that I was discussing yesterday. But then there is also energy points of higher energy, up to 104, in fact, energies, and that corresponds to the higher energy stages of running of the LEP collider. Okay, right. This is a plot that you have to have in mind if you think to resonances. Okay, this is the phase that the resonance has. An unstable particle looks like this. It's a combination of measurement of cross sections that came from LEP around here and also around here. The high energy range is also called the high energy runs are also called the LEP2 experiment, and these are previous measurements. You see the 1/s scaling of the cross section. There is the huge resonant peak. This is clearly a log scale, otherwise you would not see the peak. And then there is another 1/s square with a different coefficient, because before here there is only QED, and so the couplings are those of QED. Here there are different couplings for each for the W and for the Z, and sorry for the Z and for the photon, and they sum up giving a different slope. Here, if you want to check that, so this is number of events collected divided by thousands, and you can more or less check our cross sections times luminosity. They work for this total statistics of around millions, as you see, of events, right? In each different for many different measurement. So here I wanted to point out something. So this is in fact the high energy run of LEP, but it doesn't matter. So this is the plus E minus production, and this is the number of events for the plus E minus production. These are different cuts, okay? But for example, look, this one should be comparable, in fact, with this, okay? So this is the total cross-section from plus mu minus, which brings 177 events in this particular run of LEP at this particular energy, while the one that corresponds to plus E minus is around 3,000. Well, sorry, it's around 8,000. Okay, so well, this was just to remind myself and you that when I did my calculation here for E plus E minus to FF bar, okay? I only consider this type of diagrams with S channel, right? But in fact, if this F is an electron, then there is also these diagrams here. And well, these diagrams, in fact, have a huge effect. In the region where these E plus, E minus are produced forward, the T channel propagator is very small because the T Mandelstam variable goes to 0 when the particles are very small. And so this one process, if you look at the total cross-section for E plus, E minus, sorry, this one diagram, not the process, it dominates by far when you are in the forward region, and that's why the total cross-section for E plus, E minus is so huge and so much larger, for example, than the cross-section for mu plus, mu minus, in spite of the fact that electron and muons have the same couplings, right? But they are different particles than the initial particles. Okay. Right. Okay, and then this is a table that summarizes some of these parameters that we say can be measured at lab. So there is the mass of the Z, the most precise determination of the mass of the Z that comes still today from lab by the fact that you can just fit the position of this very high peak. And so you can measure the mass, the cross-section line shape, the peak position gives you the mass of the Z, the width of the Z. Then you have the cross-section, and in particular, we had here the cross-section, where is it? Two hadrons, for instance, that is the one used always for normalization, from which you can also extract another parameter that I don't think is reported here. Can be derived from here, which is the Weinberg angle. That's also measured very precisely by these high statistics of lab measurements, and then all these ratios of widths. I told you why you can convert the measurement of cross-section into measurement of widths, asymmetries as well, and yeah, and so there is a per mil level verification that these numbers match with the best fit of the standard model. So with the standard model, with input parameters that are measured precisely in this experiment, and they are in perfect agreement with the standard model. Okay, right. So implications, okay? Implications from the viewpoint of the standard model theory, per mil level test of the fact that the Z boson couples to fermions like gauge theory tells you. So the charges, the gauge charges are assigned to that way because of this. Are assigned that way, and then this is what shows that this is correct. The measurements were so precise that our three-level calculation does not work fully. So there are corrections that come even from loop diagrams that involve, for example, a virtual top quark or a virtual Higgs boson in the standard model. And so the measurement was so precise that one could do this calculation and have an indication of what was the value of the top mass and the Higgs mass before it was discovered. It was a large window, but still there was sensitivity to these other standard model parameters through radiative corrections. There was a long program of studying the physics of the QCD jets that, well, I will not mention very deeply, but I will tell you more later. And then, as I was saying, best measurement of the input parameters of the standard model. Implications for theories beyond the standard model. I told you that since you measure the total width, total decay width of the Higgs, and you also can measure the partial width to the different things, leptons, quarks, and so on and so forth, you can subtract them and obtain the width of the things that you cannot measure. And so the Z to invisible, number of neutrinos, or new very light particles that couple to the Z and that you cannot detect in any way, you can probe them and exclude their presence by this type of measurement of the invisible Z width. When I was young, I was struggling all my time to build models, beyond BSM models, that would not be excluded, in fact, by these electroweak precision tests. That is the fact that, again, you are so precise in your measurement that also, even if new physics is heavy, it gives an imprint through an effective field theory, if you want. It gives a small imprint on these observables, which then makes that relations which are exactly true in the standard model stop being true. And you can compute these effects together with the loops of the standard model, and you can bound these effects. And so you have indication of what new physics could have been at the LAC, right? Because then at the LAC you go at the scale which is directly comparable to this, and so it was a constraint. And furthermore, probably you don't know even what SUSY acronym means, but at some point there was this supersymmetry scenario which was considered to be extremely motivated in the 80s, and the very motivated version of this scenario would foresee new particles to be produced at LEP. New supersymmetric particles should have been produced at LEP, especially at the energy run. They were not, and so we already knew somehow that very natural supersymmetry was not there by LEP collisions. Okay, so this concludes the textbook version of lab physics. And so now we go to lab physics beyond, please. Sorry? So this reports the cross-section plus and minus into hadrons, but I guess this one means the cross-section for W plus W minus production. Okay, so it's a different process that for some reason is reported on the same plot. By the way, this is another thing, like not very precisely, but you could also measure the coupling of the vector bosons among each other. For example, in W plus, W minus production, you have an intermediate Z or intermediate photon, which then goes into WW. And by these measurements, you can access this trilinear, it's how it's called, the gauge coupling. So the textbook version is over. More questions? Please. Right. It was not possible because the Higgs, of course, you could say, okay, I produce the Higgs like the Z, I do like this, right? And then maybe the Higgs decays, and also be bad. This coupling is proportional to the UKAU of the electron instead to the -5. Exactly. Then you have something like this, then you have something like this, and then you have this. Okay? So which is associated production of a Z and of a Higgs. Now a Higgs is 125. Today we know. That time we didn't know. The Higgs is 90, and so it doesn't work. Okay? So you do have to have an energy which is in excess of 200. Like this. So now this is a three-body process, right? X to Z, yeah. This is legitimate. This is a three-body final state. And so it has a much smaller cross-section. Okay, and also if you really want to study this, then there must be an energy recoil of this versus that. So also this cross-section will be very small if you don't have enough energy. And LEP was struggling with energy because it's true that the energy is above the mass of the Higgs, but in practice, when you want to produce it, you need to produce other things that do make this energy not sufficient, not by much. And in fact, this was giving a constraint. So LEP was giving, when I was a student, bounds on the mass of the Higgs, lower bounds on the mass of the Higgs, and it was really almost discovered it, but he didn't make it, which is good because it shows how a collider that somehow failed to discover the Higgs was in fact, it's the textbook illustration of why we believe the standard model is true. So somehow the LEP not discovery of the Higgs somehow shows how non-discovering particles, in fact, is not necessarily a reason why the collider was not successful. Anyhow, other questions? Okay, so the non-textbook part. So in this plot, I'm showing the cross-section, and so this is the cross-section to hadrons, but the same will be obtained with the cross-section to muons or to electrons. Well, to electrons, as we say, it's a bit slightly more complicated, but fine. As a function of the energy of the collider. So each of these points is taken from a different run, and you go to the accelerator person and you ask why this doesn't work. And you ask, yes, where am I? Okay. So, and you ask what is the energy of collisions the collider has been tuned to? Okay. So this is this is not the result of a measurement. Let's say of the measurement in the detector is the result of let's say is the result of, so it's the energy of the beam. Okay, is the energy of the beam, and then you measure these cross sections and you report the points here, and you find this green curve here, and these are the experimental points overlaid with our Bright-Wigner prediction, and this is dashed prediction. Okay, So this is the Breit-Wigner formula, the one that we derived using so with our calculation yesterday. Okay. So you see that there is essentially very mild agreement. Okay. So there is an order 1 difference from this cross section to this cross section, from this cross section to this cross section. Of course, I told you that the precision of lab was per mil, but of course this is not even 10%, less. I mean, it's very bad, right? So this is a problem. Okay, so our prediction was wrong, and even a worse problem comes if you look at a different plot. So this is done at fixed lab energy. This is the run when the center of mass energy was 196 GeV. Okay, so much higher than the Higgs, sorry, than the Z mass. And then you measure this time the invariant mass. So this is the invariant mass of, for example, the pair of muon anti-muon which is produced in the collision. And you make an histogram out of this. And so if you are doing E plus E minus to mu plus mu minus, okay, obviously the energy of total invariant mass of mu plus mu minus must be equal to the incoming E plus E minus. So we would expect all the events to have 196 GeV energy, right? And in fact, we see a big peak here at 196, but we also see a shape. We also see a lot of events that do not have the same energy. And also we see in all plots, in all cases, a peak around here, which is around 90 GeV, which is around the mass of the Z boson. Okay. So how many of you know why this plot and this plot do not work like this? I mean, are so badly in agreement with our predictions? This plot is called the radiative return plot. No, but I just want to know how many of you know. Only 2? Really? Okay, good. Then the 2 who know, don't tell anybody, because otherwise this will spoil totally my lecture. Okay, this one and maybe also the next one, in which what I want to do is to explain why our naive, let's say, textbook, okay, prediction using simple single particle states for computing E plus E minus to FF bar, the thing that we did. So why that is wrong, and how so why instead, of course, the theory, well, of course, not of course, but so how to reconcile, let's say, our theory with this experiment. And so this is chapter 3 of the course, which is lab physics beyond textbook. And so here it is. So we want to explain this gap between theory and data. It's due to some physics effect, because everything is due to physics. So it's some sort of new physics until when we don't understand what it is, we can call it like this. And so the first thing that I want to discuss is whether or not this big problem, BP, this is a big problem of disagreement between data and experiment, is explained by an experimental effect. The conclusion will be no, okay? But you can conclude that is not only after you know a little bit about experiments at colliders, okay, experimental techniques, and what this measurement in reality means. So let's discuss this. So the big problem, the question is whether the big problem is an experimental effect. Okay. So what it means an experimental effect in the first place? Experimental effects is something which is different from a theory effect, right? As the name says, and the distinction between the two, of course, is artificial, because physics is one, and the physics that rules the detector behavior is the same physics that rules the short distance collision that we call theory. But it's interesting. It's useful to have this distinction in mind, because simply because there are different experts of different things. There are experimentalists who know about experiment, and there are theorists who know about the theory. It's difficult, in fact, to tell what is that makes the frontier between theory effect and experimental effects, right? But to me, I think it looks something like this. If you imagine to draw some sort of plane with the distance delta L in space and in time from the interaction point at time equal to 0, so the space-time point at which the particles collide, and of course the space point, which is the IP, and the time, let's say it's 0, at which the particles collide. If you write, if you draw something, a plane like this, then I would say that there is a frontier, sort of, in this plane, which divides what we call macroscopic physics from what we call, that is inside here, the microscopic physics. And if you want me to give a threshold of what is macroscopic, we can say, I don't know what I decided to write here, 1 micrometer. One micrometer is a sort of length which is large enough for experimentalists to be able to measure it. For instance, they can tell, maybe 1 millimeter would be better, but for sure 1 millimeter, they will be able to tell if a particle is emitted from the IP position or if it's emitted 1 millimeter away. That's something that they can tell for sure very well. Now, if you go to 1 millimeter, maybe it's more complicated, but that's to give you the idea. Also time, the time at which the particle arrives can be measured with a certain time resolution, which is something that maybe is comparable with this. It's some macroscopic length, okay? So what happens outside here, outside, let's say in the macroscopic region, is the detection by some detector of the outgoing particles, of the out particles, of the particles that are produced in the collision. And this is clearly, this process is of course a macroscopic process that is what experimental physicists study. So this is what is done by the detector, so detector physics. Okay, so the observation, the measurement of the momenta, the observation of the particles, and these kind of things. This happens in this direction, let's say, at positive, let's say, distances, and at positive, so at times after the collision. While before the collision, you have the initial beam, right? So the beams that I've drawn, there, right? They are, of course, macroscopic objects that arrive and collide, and they do define the initial condition for the scattering. Okay, so this refers to how the beam or how particles are prepared before the collision. So those who care about this are the accelerator physicists, as opposite to the sector physicists or experimentalists, and that's where the people you should ask with if you think that your problem is due to this part. You should ask experimentally if you think it's a detector problem, and then we are here in between, okay, focusing on this short distances effects. So let's begin from the detector, so from this type of effects here. As I said, they cannot be responsible for this failure of the prediction, but again, why not? So in the first place, at the level we will discuss the topic, which is very low, the topic of particle detectors. All particle detectors look the same. They are cylinders. In fact, cylindrical layers. Sorry. Okay, so really physical cylinders made or containing some sort of material which is in some way sensitive to the passage of particles. There are many layers, and they are cylinders with the axis, so this is of course the z-axis or the beam axis, and they are centered obviously around the interaction point. If I view this from this side, right, from the side along the beam, then I can make a more detailed characterization. Here there is the IP, and then there is a first set of layers which are very close to the IP, as close as possible you can put them, which are essentially silicon detectors that react if a charged particle crosses them. Okay, they click. They can also have timing information, and these are the tracker detector or inner tracker, inner because it's the most close to the interaction point. And so they record the fact that the particle emitted from the IP has traveled in a certain trajectory or on a certain track. The big cylinder is immersed some way in a magnetic field. So there is a magnetic field as strong as you can make it, which then exits from this plot here, like this. And so, you know, charged particles in a magnetic field, they bend. Okay, they make a circular trajectory in the plane orthogonal to the beam. And so if you have a charged particle, what's going to do is going to do something like this. So if you view it on the transverse direction, it has a radius of curvature, right, which you remember from classical electromagnetism, is inversely proportional to their transverse momentum, to their momentum along this plane, right, the PT. So if you manage to reconstruct this track, which means if you manage to take up the hits that this particle leaves, sometimes it does, sometimes it doesn't, right? The hits that this particle leaves, and you manage to connect the dots in a smart enough way that reconstructs, that corresponds to the real passage of the very same particle, then you have a measurement of the trajectory from which you can measure the radius, and then you can establish the transverse momentum. So let me write it here maybe. No, here it's too much. So roughly speaking, from the tracker, you get PT of a particle, and also, in fact, the whole particle trajectory. So this in particular means that in some cases you can tell if the particle trajectory was going through the EP precisely or not. So whether there was a displacement. So in fact, tracking allows to determine PT plus, let's say, displacement if there. Okay. Then outside there is another of these layers, which is called the electromagnetic calorimeter, ECAL. So what is this ECAL? This ECAL is a block of heavy material which is instrumented and segmented. That means along the azimuth of this cylinder, and also longitudinally, you can divide in little blocks this ECAL, like in this case will be like here, and each of them is an independent detector. Furthermore, inside each of them there is detectors, because what this ECAL wants to do is that there is, for example, a photon that comes in, and then it interacts with the material inside, and so, for example, it emits electrons, then it will emit other photons and other electrons and photons. It will do what is called an electromagnetic showering. So the QED interactions will continuously make this particle produce new particles and produce photons in particular. At the end of the process, the particle will lose all its energy, and all its energy will be left to these photons, essentially, that you need to collect and measure by some layers of detector in this direction, which tell how much energy has been lost, and also the form of this showering can be measured how much energy has been lost in the calorimeter. And so from here, you measure the energy of photons, but also measure the energy of electrons that go through a similar electromagnetic showering. So the eCal measures essentially energy of photons and electrons. Well, in fact, it also measures the angles. So let's say, or the rapidity, but then it doesn't matter. So let's say the theta and the phi angle of where the particle was going. You know it because you know essentially in which place of this cylinder the showering was taking place. Okay. Another layer that is thicker is the hadronic calorimeter, which works in exact same principle, okay, but simply by hadronic interactions. So hadronic interaction cross sections and showering is slower, so it takes longer to develop. So, for example, a charged pion would essentially go through the eCal because it has higher mass, and so it doesn't have the same huge showering that electrons and photons have, but then will go here where there is much more material, and so at the end will be stopped by QCD or hadronic showering, and that's the role of the HCal that does more or less the same energy, phi and theta, but for hadrons, such as, for example, let's say of course, for the hadrons which are stable, the hadrons that do not decay before, right? Otherwise, before reaching the hadronic calorimeter, and so, like, for example, pions, kaons, protons, lambda baryons. These are the things that experimentalists do see. Of course, they don't see, as you know, they don't see quarks. They see all these kind of things. Pi zero, they don't see the decay to gamma gamma. So that's the type of thing they see. Finally, one thing which people like to say because it's very simple is that this, for example, is what an electron will do. So an electron would make a bent track here because it's a charged particle, and it will also interact with the electromagnetic calorimeter and leave a heat here, okay, and then disappear, will be absorbed, okay. A photon would similarly make a hit in the electromagnetic calorimeter, so a photon will not bend, and so we'll just leave a track in this calorimeter, and so that's why we distinguish the photon from the electron, from the fact that the electron has bent in this, and so you see it in the tracker, that there is a bent track, and also that instead the photon goes straight. What else? The muons. The muons have a high mass, and so the electromagnetic showering is not there, right? They are penetrating particles. They go through the eCal, they go through the HCal as well. And so all what they do is little tracks, okay? They just hit the hits of trackers, and they go outside this big cylinder. And often there is additional detectors here, which are dedicated muon systems, which are outside, again, another layer, which is just dedicated to detect the muons, exploiting the fact that those are the only particles that conceivably can escape. And also to help measuring their momentum, because you can make more points with a longer leverage arm, gives you a better determination of the momentum, okay, of the muon. So it could be worth giving here some type of performances that these detectors can have, just for you to have an idea. So the tracker, as we said, measures the transverse momentum with a resolution that is of order 3% for tracks at 100 GVPT, and the resolution gets worse and worse the higher the PT. And this is easy to understand because higher PT means that the radius of curvature in the magnetic field is smaller. So this looks like a straight line. Right? And so it's more difficult to tell that it's not straight, and it's more difficult to tell what is exactly its radius. Also, at some point, it becomes difficult to tell whether the muon has charge plus or charge minus. Because if it has charge plus, it goes like this. If it has charge minus, it goes like that. But if they both become very straight, then it's difficult to tell if the curvature was in one direction or in the other corresponding to the charge. So, yeah. Let me make some space here also to illustrate that this detection, of course, is possible only in certain regions. If you have a particle that happens to go just like parallel to the beam, there is no way you can see it, because there is no way you can instrument precisely the region on top of the beam, because otherwise you will just detect all the beam particles that goes through. So all colliders are blind, for if you want, even for deep reasons, in fact, are blind to the very forward region. There are more detectors you can put here, in particular the LAC, there are the end-cap detectors to further reduce the angle at which you're sensitive, but for sure there is a maximal coverage in terms of angle. So there are angles above which you cannot see. So in the case of trackers, these are numbers from the LAC, more or less, but the pseudo-rapidity, this quantity I told you, is associated with the angle for massless particle. So pseudo-rapidity, for which you can do tracking, is smaller than 2.5, which corresponds to around 10 degrees. While the calorimeters are installed covering total the region that goes from covering in total the region eta smaller than 5, that corresponds to instead 0.5 degrees. Sorry. Very small angle, but still finite. In this case, the resolution, delta E over E, the resolution on the energy, you can estimate it as 1% or 5% for the each cal, or for the electromagnetic or hadronic calorimeter, but they scale the opposite way, with the square root, in fact. So at 100 GeV divided by E. So the resolution becomes better the higher the energy. And this, if I remember correctly, my classes undergrad, is because this showering is a statistical process that occurs then in bits. And the more energy you have, the more bits you have. So the more steps you have to go through the showering. And this reduces the statistical uncertainties. Okay, this is something like 1 over square root of the number of events. Right. Let me show you again the okay. So now we have a view of how the detector works, and also we can have a better view of what are these cross sections that experimentally do measure, how they are experimentally defined, and if in there can be something that can help us explaining this plot. So let's for instance consider the cross section for F equal to electron. Okay, we can correct for these effects that there is a forward photon. Let's consider the electron. If you consider the cross section, sorry, for electron, how it is measured? Well, we said electrons are those particles that bend in the tracker, that leave a hit in the electromagnetic calorimeter. We can measure, by the way, their energies and momentum. So if we want to be sure that, so then what we're gonna ask is that there is an E plus and an E minus in the event, which then will bend in opposite direction. We will reconstruct this trajectory. You will know where the hit of the calorimeter is. We will combine this information, and we will conclude that the event was characterized by an E plus and an E minus that are more or less back to back. So the cross-section, for example, for fermions, FF bar of the electron type, is measured by just counting how many events have E plus and E minus, where the presence of the E plus or the E minus, once again, is then at the let's say, detector level, it's represented by a number of, by a specific output of the detector, a specific outcome of the detector along the lines I have discussed. So in general grounds, when we speak of experimental effects, we worry often about the efficiency. That is to say, we decided that the event was an E plus E minus production based on some properties of the observed configuration in the detector after the collision. But how many times, if you really have E plus E minus, you do get a hit with this strategy? Sometimes you can lose the electron. Sometimes you may fail to reconstruct the track. Sometimes, I don't know how rarely, but the electron could even not make a shower. It decided to go through. I don't think it's possible, but this can happen. So there is a probability. So I think that generically for the LAC, and I think it was higher for LEP, this is relatively high. So the efficiency is around more than 85, 90%, or even more. That is to say, really the vast majority of times, if you have an E plus E minus, it will be seen as an E plus E minus. That's what efficiency measures. On top of this, if I look at this plot, then you see, if there is an efficiency, which is much lower than 1, if I lose many electrons, everything will change, is that the measurement will be wrong, because instead of, so will be wrong by multiplicative factor. This measurement is just the number of events divided by luminosity. The number of events was underestimated a little bit, and so this curve will just go down, but will not change shape. Cannot change shape, okay? Also because, of course, for all these points, the same detector was used. It's just the energy of the collider that was changed. There is no way in which efficiency can be different in one run or in the other. You may say, okay, but there is uncertainties in the measurement of the energy of the photon or the electron. They are very small, and furthermore, they are not shown here. So in this plot, as I say, there is no measurement of the energy of the electron. There is just, in this axis, there is just the beam energy, not the result of that measurement. The measurements are just used to define what is the vertical axis, so to compute this cross-section. Another thing you have to worry if you want to study experiments, generically, is fakes. That is to say, sometimes you do see a signal in the electronics of the detector, gives you a signal that is exactly identical to the one I described for E plus E minus, but it doesn't come from E plus E minus. I don't know, quark, anti-quark, somehow two jets. For some reason, you see just one single charged track of a pion that then for some reason goes only in the magnetic calorimeter. So everything can happen at a certain low probability. This is very low. I then found an estimate, but at the LEC, mistagging an electron, so even jets, which are, yeah, I mean, it's really below per mil. I don't know what to write here, but it's really, really small. But even if it was not smaller, it cannot change that plot once again, because the Bright-Wigner shape is universal. Any type of fermion you produce, you will get the exact same shape. 1 over E minus m square minus gamma square m square. That's true for the quarks, it's true for the muons, for the electron. So even if there are fakes, that is to say, if sometimes here you have erroneously counted events that come from jets rather than coming from electrons, this will not change. Will change the normalization, can make this curve go up and down, but just a scale factor. It cannot change the shape. Okay, so, and very similar consideration hold if you look at muons. Okay, the experimental signature is different, but again, it's very simple. In this case, it's even simpler. You just see some tracks. You don't see hits in calorimeters. You see a track outside, maybe, if there is a muon system. Yeah, not much to say. If you have tau leptons, situation is different because the tau lepton decays. It's a bit more complicated. I will not discuss tau leptons, even though they can interestingly provide, for example, polarized measurement of cross-section at LEP, many nice things, but we can simply ignore this case, okay, for the time being. Okay. Even if by now we are convinced that this cannot be explained by the experimental effect, let me tell you something more about quote unquote measuring quarks, very much in quote unquotes. That is to say, among the processes we computed, there are those in which the fermion is a quark, for example, so which can be an up, a down, a charm, a strange, or a bottom. Why it cannot be a top? Oh, yes, the mass of the top is too much, right? Okay, but then so the mass of the top is how much it is? 74, no? 72 point. But anyhow, it's lower than 200 GeV. So we know we have this run at 200 GeV, right, of LEP. So then why then you cannot? You must produce two top. You cannot produce, I don't know, top anti-up, because flavor transition in the standard model are very, very small. Okay. Right. Right, so these are the quarks that we produce in our theoretical calculation, but then what is that we observe? For sure, we don't observe these quarks. So the discussion here of jets will not be satisfactory. There will be something more in the next lecture, but just to give you some minimal information. That is to say, what we do see, okay, in experiments, in detectors like that one, are called jets, and these are collimated sprays of hadrons. So all these lines are pions, kaons, lambda, protons, gamma-gamma pairs that come from the decay of a pi zero. Everything that looks like a hadron has to be reconstructed, and then it forms a list of particles that experimentally gives you and forms a jet. This is one jet, and this is the other jet. And so very, very superficially, you can think that jets are the experimental representation of quarks. That is to say, there was a QQ bar that was produced with a certain theta angle. You will get two jets with the same theta angle if you define the jet momentum as the sum, of course, of all the momenta of all these hadrons here and there. So in first approximation, you can think to jet particles, which are composite of many other different particles, composite in the sense that they are built, their momentum is built by summing up different particles, and identify quarks with jets. There is way more than this. It's a deeply theoretical subject before than experimental one, but this is the naive intuition you can have in mind when I say that experimentalists can measure the QQ bar cross section. In fact, to be more confident that what we are doing is correct, let me point out that for this specific measurement in particular, this sigma hat, in fact, we don't need to speak about jets. So it's interesting to speak about jets, but jets are not needed to measure and to predict this sigma had, because sigma had, this hadronic cross section, is the total cross section of E minus E plus going to any set of hadrons. One, two, several, of any different possible type and species and pions and protons and all possible things that you call hadrons are counted. So to measure that thing, what experimentalists did, they just tried to make sure that there was not very energetic electron and muons and photons or non-hadron particles in the sample. So they just essentially relied on hadronic calorimeter, on tracking for the charged hadrons, and they just wanted to make sure that that event contains, okay, most of the energy of that event at least is brought by hadrons and not by leptons. And so they didn't need to reconstruct the jets. If they had looked at their events, they would have seen, in fact they did see in this study, or if they wanted to compute the asymmetry, which requires angular information or angular distributions like theta, then they would have required jet physics. But they didn't require jet physics to do this measurement. And from the theory side, one of the most simple and also important results of textbook QCD physics is the fact that the cross-section for a plus and minus into hadrons defined inclusively, summing over all hadrons, as I'm doing here, let's say, is, well, it's safe, but let's say is perturbative. Which means that it can be theoretically computed as a theoretical cross-section of E plus, E minus going to QQ bar, exactly the calculation that we did, to which you can, if you want, add things like E plus, E minus going to QQ bar plus a gluon, or 4 quarks, or 2 gluons, QQ bar, and so on and so forth, all possible final state that contain quark and gluons should be added in line of principle to the theoretical prediction, but this one is the one that dominates. That's why it is perturbative. These ones are suppressed by alpha strong with respect to this one, and so this that we computed at 3 level is a good approximation, in fact, of the hadronic cross-section. This is one of the few cases in which this result can be proved rigorously, okay? And so it's pedagogically very interesting. In his small book, for example, the one of Peskin, have a discussion that it's quite satisfactory. And intuitively, okay, it's based on a fundamental property of QCD, which is this duality between particles and particles, so in the sense that if you do produce QQ bar, all what these things can do is to produce hadrons. They are obliged to do so by color confinement. Hadrons, on the other hand, can only come from QQ bar. So if you just are interested in the probability of producing any hadron, okay, then this can be computed as the probability of, quote unquote, producing any parton in any possible configuration. And so that's the reason why, the intuitive reason why this is true. Yes. Central mass energy are below lambda QCD. Well, you don't produce many hadrons, right? So if the center of mass energy was below lambda QCD is, let's say, 300 MeV. It corresponds to the mass of the hadrons. So producing hadrons in below that threshold is impossible by kinematics. QCD is a gapped theory, so yeah. Right? And it's true, but sorry, I think you made an interesting comment in the sense that this is true, okay, this is true. The perturbativity, okay, of course must be accompanied by the perturbativity of the QCD theory itself. So this contribution is over the alpha strong, but if the process takes place at too low energy, alpha strong itself is big. And so the formula in the end, this formula will not hold, right? So we are at energies of 100 GeV. At this energy, alpha strong is a perturbative coupling. Can give 10% corrections to this. I am not saying that it can be fully ignored, but I'm saying that it can be 10% corrections to our formula, but not more than this. And also this correction will have the same shape, because the shape is dictated by the Bright-Wigner and not by QCD effects, I think. So we did almost everything about detectability of things. with one exception that I want to discuss. It's the bottom quark. So from that discussion above, it's completely obvious that you cannot ask experimentalists to measure the cross-section for the plus and minus to up anti-up or down anti-down, okay? They don't know what the up and the down looks like experimentally, and in any case, we will not know. So it's something that we can compute, but of course cannot be measured. It's not physical. Instead, you can ask the question of what is the cross-section of E plus E minus to BB bar, B being the bottom quark, and yeah, I erased it, but and in fact, if you look at this table of lab performances, there are these are there? Ah, no, they're not there. Fine. RB, they're not B, no, B, they didn't carry this table. Fine, but lab measured the cross-section for BB bar, and also this allowed lab to study the couplings to the BB bar individually with respect to the coupling of the other particle, for example. Yeah, okay. So this can be measured. Why it is so? It's because of the following. So the lifetime of a bottom quark, the bottom quark decays. Right? So the lifetime of the bottom quark is around 10 to the minus 12 seconds, which if you convert it in length, it's around 1/3 of a millimeter. Sorry, not a meter, millimeter. So this tau, bottom, is in the first place much longer than the typical length scale of QCD interaction, which is of the order of 1 femtometer. Okay? Which means that the bottom quark, once it's produced, using a naive time picture, will travel and will immediately be surrounded, okay, by hadrons that come from the vacuum, okay, QQ bar that come from the vacuum, and it will immediately, in a very short time scale, let's say, form hadrons like B hadrons, B plus, B minus, so hadrons that contain a bottom quark inside, okay? These hadrons then will have a lifetime which is the same as the one of the bottom quark, and so they will keep alive, and so they will travel for a long distance of the order of this c times tau, if they are produced nearly at speed of time, of the order of 1/3 of the millimeter. So if you want to measure, so to measure the cross-section for bottoms, you need to be sure that the bottom has been produced, and you can be sure that in fact the bottom has been produced, because what you will see is that you will have a collision event. The collision event will take place at the IP, at the interaction point, at this point where the particles hit. But then you will have particles that come from the decay of the B hadron, B decay products, that give tracks, that give trajectories that do not intersect on the IP, but intersect at some other point in space, which is far from the IP of the order of 1 millimeter, which is a good macroscopic distance that experimentalists can tell apart from IP. They can tell that this is not happening at IP. And this is what is called a displaced vertex. Okay? And so that's why we can measure the cross-section to BB bar. Okay, if there are more questions about experimental, so you can ask them anyhow, anytime, but now I'm gonna leave the purely, let's say, experimental considerations, because I think I made a good enough job to convince you, now that we know how the experiment is performed, that it cannot be responsible for this big problem. But still, the big problem could be a beam effect. Which is to say, in this graph I had before, there were things happening after at microscopic times and distance, but also things happening before, the way in which we prepare the beam. Okay, so this will be, again, not a theory effect, but it will be a experimental effect, or if you want, a beam effect. Okay. So it's not inconceivable, because I told you that the vertical axis in this plot is very safe, experimental input, while the horizontal axis is coming from the beam dynamics people. They tell me that this energy at this point was 88.2. But maybe it was wrong. Maybe the problem here is with the horizontal axis. This could also, in principle, explain this plot here, because you have all these events with an energy that is not equal to the collision energy. But so maybe when collisions occur, right, if they occur collision between these two bunches, which are made of many different particles, that of course not all of them have the same energy. So maybe this spread is due to the fact that the energies of particles in the beam is not exactly equal to half the center of mass energy. It's not exactly equal to 45 GeV. Okay? Each particle will have its own little different energy distributed on a statistical basis. This is a phenomenon that can happen, and it's called the beam energy spread. Okay. Also, this one is not going to be the explanation, but it's very instructive also for the true explanation to compute this effect. So essentially, what I'm saying here is that the true energy of an electron that is colliding, which is one of the ones in the beams, randomly sampled, is not the center of mass energy divided by 2. Remember, this is S, so it's not square root of S or ECM or square root or ECM divided by 2, but it's there is it's variable, and there is a statistical variable x that can be different from 1. Okay. So inside this beam of particles, there will be a distribution of energies corresponding to a distribution of x, okay, around x equal to 1, that corresponds to the nominal beam energy. I'm going to call f of x the probability distribution function for this variable x, which is then the distribution of the energy. So literally, this is very well defined, simple statistical concept. So f of x times dx is the probability that the particle in the beam has an energy which is not equal to ECM over 2, but it's in a narrow window around s over 2, x plus delta x square root of s over 2. Okay? Right. So this effect is there, and beam physics can in fact measure for you, or compute, in fact, or simulate this f of x distribution. And so to some level, in fact, it has to be included in the predictions, even though it's not going to be the explanation. What this means from the viewpoint of our theoretical prediction is that when we did the calculation, we thought that all particles had, all of them, always the same momentum. But in fact, now the particles from beam 1 has a 4 momentum. I'm going to take the limit in which the electron is massless. So it's going to be x1 times square root of s over 2 times 1, 0, 0, 1. That's the particle that moves on the plus direction of the z-axis, while p2 is going to be x2. Of course, another instance of x sampled from the same distribution, if the distributions are the same in the two beams, as it is the case, x2 square root of s divided by 2, 1, 0, 0, 1. I'm going to use light cone coordinates, which are more convenient. So in these light cone coordinates, which means that the momentum is expressed as p plus, p minus, and pt. P plus minus is equal to E plus or minus P3. Then you do have that P1 is x1 square root of s, so it has a P plus of x1 square root of s. It has a P minus that is 0, that's because it's a nearly massless particle that is moving in the plus, so along the z-axis, parallel to the z-axis, and of course 0 transverse momentum, while P2 has 0 x2 square root of s, 0. Okay. So this makes that now the total momentum, which is the total momentum of the center of mass frame, that is previously called P, and is P1 plus P2, now is not at rest, okay? So the center of mass frame, so the lab frame is not in the center of mass of the collision, but it's in fact given by x1 square root of s, x2 square root of s, 0 in the transverse direction. So that is to say, the center of mass does not coincide with the lab frame, and we call y the rapidity of the center of mass, which is, as we saw, 1/2 the logarithm of p plus divided by p minus, which is 1/2 the logarithm of x1 divided by x2, right? Also, before, when particles were colliding, they all had the same square root of s, right, ECM. Now, instead, the Mandelstam variable that corresponds to the true collision of the particle, we call it S hat, just to distinguish it from the nominal center of mass energy S, which is going to always be kept fixed, which is going to maintain the same name as before. So S hat is P square, and it's x1 times x2 times s. And so it is convenient to define a variable tau that is x1 times x2 and write this as s hat equal to tau times s. And so, like, you can conveniently use these tau and y variables to express x1 equal to square root of tau e to the y, x2 equal to square root of tau e to the minus y, which comes very easily if you invert these relations. No, maybe go like this. We are going to put a hat on top of the cross-section, of the new cross-section that we need now, sigma hat. So this sigma hat now is the cross-section for this process. There is an E minus that has a energy x1 times square root of s over 2. Okay, so let me call it like this, E minus x1, E plus x2, which goes to ff bar. Okay, while previously we only computed the cross-section for x1 and x2 equal to 1, but it's very easy to obtain the new cross-section because we are in the limit where all these particles are massless, so the cross-section is perfectly boost invariant, and so first we can write that sigma hat is equal to sigma hat for the process in the center of mass frame, E minus E plus in its center of mass frame. And so we already computed the cross-sections in the center of mass frame, and so this is our previous formula for the cross-section, but evaluated at center of mass energy square equal to S hat rather than S, and this can be expressed as tau times S. Okay? Just reusing the previous calculation, just taking into account that now the energy in the center of mass is not S, but is S hat. So you take the previous formula and you obtain the new cross-section. So what is then that we do have to give to our experimental friends if we want them to make the right plot? So we have to give them the cross-section, not sigma hat, which is the following. There is probability dx1 f of x1 and dx2 f of x2 that the initial collision was taking place with x1 and x2 energy fractions. And so when this is the case, okay, then the probability of reaction, which for us is the cross-section, is sigma hat of x1, x2. Let's say a priori is this one, a cross-section that depends on x1 on x2. But in fact, we saw here that it's just a function of the product. So we just have sigma hat of tau, which is x1 times x2, x1, x2 times s. This suggests us to change variable, and so we have the integral in tau and y, so you can check that the Jacobian is 1. You can write this as the integral in tau and y of f of square root of tau e to the y, which stems from x1, f of square root of tau e to the minus y, and then sigma hat of tau s. And since the cross-section does not depend on y, I can do the integral on y and define and write down everything, which, okay, as integral d tau of some function that I call differential luminosity, dl over d tau, times sigma hat of tau s. dl d tau, differential luminosity, is the integral in y of the part of the PDF square root of tau e to the y, the PDF square root of tau e to the minus y. Okay? Now, beam physicists can measure these f's. They are very much Gaussian, okay? And so this luminosity is also Gaussian. So we can take dl over d tau to be 1 over square root of 2 pi times delta e to the minus tau minus 1. It's a Gaussian centered around 1, of course, which is the point that corresponds to nominal beam collision energy, squared, divided by 2 delta square. And this delta is also known as delta BES, and it is the beam energy spread. They will tell us later how much it is. It's Gaussian and it's narrow, which makes that then whatever you do with them is always a Gaussian. So let's just pick up a Gaussian for the part of luminosity. So what I want to do, and what I did in a notebook that you have also on the GGI webpage, Mathematica notebook, maybe it's too old-fashioned for you that use Python, but okay. I also use Python, but I prefer Mathematica. I wanted to make this calculation. So we know this sigma hat. We can make, this calculation at this level here, in which we do this. We can do this integral. We're going to try to predict the effect of this smearing in the beam energy spread on the observed cross-section. I did this calculation by a Monte Carlo integral. And clearly, Monte Carlo integration and event generation is one big chunk of things that people does in collider physics. And I think this one is the first good reason you can encounter to do such integral, because we have to integrate, in particular, to convolute a Gaussian with some theoretical function that we have computed down here. I think if you study Wikipedia, you will learn about Monte Carlo integral as much as what I have time to tell you now. But here there is. So we can have typically multidimensional integral. Tau in general can be a multidimensional variable. That's where these techniques are mostly useful. And we want to compute this integral. We want to compute the integral of a certain function tau over a certain measure of integration d mu tau. So d mu tau is explicitly some d mu over d tau function times d tau. Of course, what we need is an integral, like here, it's the total, it's everything, it's the product. So how we split this and that, it's arbitrary, and in fact, there can be better or worse choices. But for us, we are just gonna say that, of course, the d mu over d tau will be identified with the differential luminosity, and the function f of tau to be integrated is our sigma hat of tau s, is our cross-section. One can better formulate this thing by using a measure which is normalized to 1, such that the total integral in d mu must be 1, which means essentially that, well, basically that integral d tau d mu over d tau, right, is equal to 1, which is like in our case where this is just it's just a distribution function. So it's a Gaussian, it's normalized to 1. So the Monte Carlo integral is a very simple thing. Yeah, you construct a sample of instances of tau, which is sampled according to the distribution d mu over d tau. So for us, this will be Gaussian. So I will throw Gaussian distributed numbers, and I will put them in some list L. So I will have tau 1, I will have the first value, I will have the second value, up to the n values of tau. Then I will estimate the integral I as I hat, which is the mean over the list L of the function f, which is literally 1 over n, total number of points that I've generated, sum over I, which goes from 1 to n, f computed at tau I. This is evidently a good estimate because by the law of large numbers or the central limit theorem, you know that when n goes to infinity, averages become expectations. So this thing will become the expectation with probability density of, or with probability measure of mu of f of x, or f of tau, sorry. And this is then just integral d tau d mu d tau f of tau, which is precisely what we want to compute. If you like, and in the notebook there is also a check that the error estimate work. So the error that I make when I do this is 1 over square root of n times square root of v, where v is the variance of the variable, that is to say 1 n f of tau I minus I hat squared. Okay? Right. How many of you have taken some classes that teach you how to do a Monte Carlo integral or similar numerical type of things? Good. So maybe I can go faster and next one. So this one is the result of this little Mathematica notebook by including a beam energy spread at the 1% level or the 2% level. You see, it doesn't work, right? It doesn't work. So 2% is reasonably good in the sense that at least it makes that this peak has gone down, like here, similarly to how much has gone down there. But you see the shape is completely different. This is broader than the initial peak, and this must be because we make a Gaussian smearing, so we further broaden the peaks, but the same on the left and on the right. It's just broader in both directions, while this one is going down here and is going up over there. It's asymmetric. Doesn't really work very well. You may say, maybe the beam energy spread is not Gaussian. Maybe I can go and I can tune this the differential luminosity distribution until when the plot works. And maybe I can, in fact. If I look at this other plot here, the situation is even more clear. However, it's even more clear that beam energy spread cannot absolutely explain what we have seen in the data. Before telling you why, let me take the last 5 minutes to explain how this plot is obtained. This plot is obtained by, This plot is obtained by employing simulated events. That is something that we really do all the time when we work on collider physics. So this is a simulated event or a Monte Carlo sample, and it's made of the following. So you take our list L of tau1, tau n generated points, and then you join it with a list that we call the list of weights, which is W1 to Wn, which are just the function f, that is to say the cross-section, evaluated at the points that you had sampled in the list L. And so a Monte Carlo event is an object, so it's a list made of events. So a Monte Carlo event sample is a list made of Monte Carlo events, which are objects made of pairs, like here, tau I, wi. Okay. This is somehow, in general, what describes the kinematics of the kinematical configuration that you are probing. For us, it's just a tau variable, but it could be the full force momentum of all particles in the event. And wi is the weight associated to that event. So this is a good thing to do because exactly by the same formula up here, the central limit theorem. If now I compute something like the mean over the list L of f times O, where O is any observable, let's call it observable, O is any function of the variable tau, this mean, which is 1 over n sum over I equal to 1 n f of tau I, O of tau I, okay? By the central limit theorem, this is a good approximation of what? Of the integral in d tau, d mu over d tau of f of tau, O of tau, okay? And this quantity here is nothing but the weighted mean, so 1 over n, sum over I equal to 1 n wi O of t con I. So Monte Carlo samples are useful because if you want to compute the things like the expectation, okay, of some quantity, like the expected value of the PT or whatever you like, you put it here, you would like to compute this integral, and you do this by a weighted average using as weights the value of the cross-section calculated at the points that you had sampled. In order to make that plot, what we need is the following. So in order to make the plot, we need just the cross-section in a bin, which corresponds to an observable O of tau, which is 1 if tau belongs to the bin. So specifically, what I mean by bin here is each bins of this histogram. So it's a certain region, okay? It's a certain region on the invariant mass M of the final state particles, FF bar, which is square root of 2, sorry, square root of s times square root of tau. Okay, so beans in this variable, a certain window in this variable, the O is 1, otherwise it is 0. And so if I want to compute the cross-section in the bean, right, this is equal of the integral to the integral in d tau in the bean of dl over d tau, the part of luminosity, times the partonic cross-section, tau s, which then is equal, of course, to the integral in d tau of O of tau, of this binary observable, times dl over d tau, sigma et of tau s. Okay, and this can be expressed as the average, so 1 over n, sum over tau, so the sum over the events, but there is the O that tells you that you have to count only those events that belong to the bean, and you have to sum the weights that corresponds to that event. So it's the sum over the weights for those events that live into the bean. Okay, it's a weighted histogram, simply. Okay. Yeah, and this guy gives us the differential distribution in invariant mass of the final state. For this specific calculation, I'm doing mu plus mu minus. That's why it's called m mu mu. And you see, yeah, that you have a certain spread, of course, a Gaussian spread, also in this case. But you really don't populate at all this region, and there is no way you have events around this mass here. Okay. Again, you may say, okay, maybe I change this part on luminosity, I make the peak appear, right? But there is a very sharp argument why. So you see, if I want to produce an event that has, for example, 90 GeV mass, right? I need the plus E minus to have, let's say, 45 GeV each, let's say, or E plus a little bit energetic, but yeah. Now, for this plot, I remind you, the beam energy, sorry, the center of mass energy of LEP was tuned to be 196 GeV. So the collider ring, the magnetic field, everything was tuned in such a way that particles that circulate here, okay, that particles with an energy ECM over 2, okay, of order then hundreds of GeV, and not 40, particles with this energy, okay, are in a magnetic field setup such that they can circulate. Okay. If I put in the LEP beam a particle which has half this energy, which has, I don't know, 40 GeV, okay, that's gonna be, that's too little energy. The magnetic field is too strong. This particle will immediately exit the beam. Okay. So it is really mathematically completely impossible that in these bunches there is electrons which have, I don't know, half of the beam energy. And then whatever this part of luminosity distribution really is, it cannot have a tail that goes up to 50 GeV. There cannot be physically electrons which have 50 or 40 GeV energy in the LEP beam at the 196 GeV run. Okay. So this is, I mean, this is obvious if you know collider physics, but it's also completely clear and unmistakable. I went pretty slow today, but fine. So at least we are ready tomorrow. Now that we have excluded all the possible explanations that we may not care about because we are theorists, right? We have to go and discuss what is the explanation of this big problem of LEP, this one and this one. And this will have to do with the effect of QED radiation. It's an eminently theoretical effect that we will be able to compute and match the data. Okay, see you tomorrow. Yeah. So, in fact, yes, we do have two different type of things. Well, yeah, see, we do have, there is a spread, of course, also in the angle that the particles have when they approach the interaction point. And so this is called beam angular spread. Okay. Now, it's a bit more difficult to model in the sense that now, before we could just recycle the previous calculation, but just changing the center of mass energy. But now it's also the fact that the particles are not exactly colliding head-on. They are not moved along the z-axis, so it's a bit more cumbersome to make the good simulation of this effect. But yes, you do also have this effect. And also, well, for experimentalists, it's also important that you do have, in some cases, it can also be important that there is a sides in the case of the beam, right? Such that the collision can happen in the transverse plane, can up and down, or so the IP is defined with a certain uncertainty in space, not only in momentum. Big problem. Big, very big. 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 Big problem. Of course, it's not a big problem like the cosmological constant problem because it's been solved, right? But until you solve it, it's still a big problem. Sorry? No. That's a B anomaly, but it's gone.